formulas, and we consider two particular cases when we apply these formulas to compute the derivative of a function f of x equals to x cubed. We consider this example, f of x equals to x cubed. The real value of the real derivative is 3x squared, and we estimate the real value of the derivative using these two formulas. Okay. And this is a graphical interpretation of the formula for numerical differentiation 3-point formula. And again, let me explain why this formula is called 3-point formula. It's written here that the derivative, the slope of the tangent line, equal to 1 over 2h times f of x0 plus h minus f of x0 minus h, and there is one hidden term, the value of a function at a point f of x0 with coefficient 0 plus 0 times f of x0. So actually, there are 3 points: x plus h, x minus h, and x. Only this coefficient f of x0 with coefficient 0. That's why this term is eliminated. You can see on the picture these 3 points. That's why this formula is called 3-point formula, and this formula is called 2-point formula or forward difference formula for finding numerical differentiation. And now let's consider one of the formulas for second derivative. Because these formulas, let me reproduce it here again. S prime of x approximately equals f of x plus h minus f of x over h. This is a 2-point formula, and f prime x approximately equals x plus h minus x minus h over h is a 3-point formula. But these formulas allows us to find numerical approximation for the third derivative. But sometimes the task is to estimate the second derivative of a function. And we can get this estimation on the basis of Taylor's theorem. Here you may see two particular cases of Taylor's formula. The first case, the formula is written for f of x plus h. F of x plus h equals to f of x plus h f prime x plus h squared over 2, the second derivative, plus h cubed over 6, the third derivative, plus the error term. the fourth derivative, h power 4 over 24 at some inner point c1. And the same formula, but for x minus h. In this case, these two formulas differs just in the sign of h. Let me open for full screen. In the sign of h power 1, h power 3. Because here, when we have h square, positive h square gives us h square, negative h square gives us h square. But when we have plus h becomes minus h. Plus h cube becomes minus h cube. And if we add these two formulas, just the first plus the second, and after some rearrangement, we can get that the second derivative at a point x equals to f of x plus h minus 2f of x plus f of x minus h over h squared minus h squared over 12, fourth derivative at a point c, where c again it's some unknown point between x minus h and x plus h. Finally, if we eliminate the error term, we get that the second derivative at a point x approximately equals to f of x plus h minus 2 f of x plus f of x minus h over h squared. This last formula gives us approximation for the second derivative of a function. Again, let me just rewrite this formula on the board to compare these formulas. Numerical differentiation f prime 2 primes. The second derivative at the point x approximately equals to f of x plus h minus 2 f of x plus f of x minus 2 over h squared. Again, if we have some point x, if we know the step h, if we know the value h, we can compute approximation to the real value of the second derivative. Let's apply this formula to our first example, to our first case. X power 3. X power 3. Let's take f of x power 3. Let's consider x equals to 1 and h equals to 0.1. Like we did on previous lesson. H equals to 1. Sorry, x equals to 1, h equals to 0.1. First question. what is the real value of the second derivative of this function? We have a function f of x equals to x cubed. What is the real value of the derivative at a point 1? First, you should find the real second derivative. How to find the second derivative? You should find the first derivative, and after that, derivative of the first derivative. First derivative we find on previous lesson. What is the first derivative of this function? The first derivative is 3x squared. The second derivative will be the first derivative of this one, 6x. The real second derivative is 6x. And if we consider the point x equals to 1, the real value of the second derivative, what is it at a point 1? Just 6. Just 6. So it's precise real value of the derivative. Second derivative at a point 1 equals to 6. Well, now we know the real value and we can compare the estimation that can be computed using this formula. Let me denote it as a formula with star. Let me mark it with star. So let's apply the formula star to find the approximation of the derivative at a point x equals to 1 using step h equals to 0.1. What we should do? We should compute the value of the function at a point f of x. It's just 1. F of x plus h, f of x minus h, and after that substitute into this formula. Please do it and find their value of the second derivative using the formula star. F of x equals to 1. F of x plus h equals to 1.1 in cube. F of x minus h equals to 0.9 in cube. Please compute the real value, not real, but the approximated value of the second derivative. You can use computer, of course, you cannot compute in mind 1.1 in cube. Use your calculator on the phone. Use calculator on computer. Of course, it's hard to compute 1.1 cube. Just in mind. You can use your phone, or use a calculator on your computer. If we try to apply this formula, the second derivative minus 2, this is the middle part, just minus 2. What is f of x plus h? We compute f of x plus h on previous lesson. This value should be written in your papers. What is the value of f of x plus h? 1.1, 1.1 and q. But don't overage. Look to the formula. Not h, but h in square. H in square. 0.1 in square. H square. H in square equals to 0.01. Don't forget to raise the h square. Well, here, what is the value of f of x plus h? 1.331. And here, f of x minus h, 729. 0.729. Okay, and if you carry out all of these operations, you will get 6. You will get 6. You will get 6. Okay, and maybe let's consider some other example. Let's consider some other example. So this is the first example, and let's consider another example. Let's take the function e power x. F of x equals to e power x. This is a very good function in computer mathematics. What is the derivative of e power x? the same function. It's very, very good function because the derivative equals to the function. The second derivative, again, will be e power x. It's a very good function from the point of sophistication. So the second derivative is e power x. And let's apply the same formula again for x equals to 1 and h equals to 0.1. How to find the second derivative at the point x? It will be e power 1.1 minus 2e plus e power 0.9 over 0.01. The value of e you can take on your calculators. I don't know. Is it available on the phone? But on the calculator in Windows, you can 719. This is the value of e, the precise value of e, but it's available in this calculator, and you can raise it at any power, for example 1.1, and get this value of 3.00416. It's enough to write just a few first digits after decimal point. And according to this formula, according to the real value of the derivative, the second derivative at the point 1 will be e, that equals to 2.7. Let me reproduce the value of e again. 2.71828, and so on. This is a real value of the second derivative at a point 1. Please compute the approximation to this real value using this formula. Of course, you can use your calculator to compute e power 1.1, e power 0.9, and it's enough to use the first 6 digits after the decimal point. Of course, these computations are a little bit complex than for x power 3. But this example shows you one feature of the formulas of numerical differentiation. enough, just 6 digits, not all digits, but that's right for you have I think it's correct. 2.72, 2.72, 0.54. 2.72, 0.5. So, of course, I don't know the exact answer, but this answer seems correct. Did you get the same? No. No? Or not yet? Well, let's discuss about these two results, these two cases. This is example number 1, case number 1. This is case number 2. What is the main difference between these two cases? Here, the exact value of the derivative is 6, and the formula that in theory gives us approximated value gives us the same value, 6. In this case, the exact value is E, 2.718, and so on. And this formula gives us the value that is close to the real one, 2.7, and the difference is at the second digit after decimal point. So this value is close to the real, but it differs from the real one. In this case, the formula gives us the exact value. Why? The answer is written here on this slide. Please look to the formula marked with star. This formula, in theory, cannot give us exact value. We can compute only approximation. What is the error of this approximation? The error is written here. Let me denote this formula as a 2 star. Please, let's compare these two formulas. This is the exact equality. It equals second derivative equals to this first term, and the second term is error. And let's look to this error term. You see that this error term depends on h square, and we discussed about it that if we take h, the small value, the error becomes smaller. But moreover, these error terms includes the fourth derivative of a function at some point. You see that the derivative depends not only on h, but also depends on the fourth derivative of a function. If we consider the function x squared, what is the fourth derivative of this function? Fourth derivative. This is the first, this is the second, the third derivative. The third derivative. Third derivative will be 6. It's a derivative of this one. 6, third derivative. Yes. Fourth derivative? No. Derivative of a constant? 0. It's 0. Derivative of a constant is 0. It means that the second term will be 0. Fourth derivative is 0. H is not 0. H is 0.1. Again, the error depends on two terms, h and derivative. H is not 0, derivative is 0, and we get the exact value. But in this case, case number 2, what is the fourth derivative of e power x? The same function, e power x. First, second, third functions will be the same. It means that it never will be 0. And this error term never will be 0. H is not 0, and the fourth derivative is not 0. It means that this formula for the function e power x never gives us the exact value. It can be closer and closer to the real value when we take the value of h smaller and smaller. But this value will be never equals to 0. Well, do you understand it? So this is a 2 star, the exact equality, and it includes the error term. This error term may be 0 only when the fourth derivative is 0. In all other cases, this error term will be not 0. Well, now I want to show you how these formulas can be applied on computers. Because you apply this formula using pen and paper, let's consider how it can be used on computer. I write a very simple program that computes the derivative of some function. Let's consider the function f of x. For example, it can be sinus. What will be the first derivative of sinus? It's cosine. So the function df corresponds to the derivative of sine, df, a cosine. Now, let's compute the approximation to the first derivative at the interval from a to b, when a and b are given values, and estimate the largest error. Again, let me explain here on the board. So the goal of this simple program is to take some interval from two given values, a and b, and here we consider a lot of points with a step h between them. Suppose it will be x, x plus h, x minus h also is a given, h is a given step, and using this grid, we compute the first derivative of a function f of x at any point between a and b with a step h, and compare our approximation with the real value of the derivative. Real value is df of x. How to do it? Let's assign a and b, for example, 0 and 1, h equals to 0.1. After that, let's write a simple loop. While x smaller or equals b, so the x is a point between a and b. We start x from a, x equals to a, and we compute approximation. To compute approximation of the first derivative, I use the 3-point formula for the first derivative, f of x plus h minus f of x minus h over 2h. The formula for the first derivative using 3 points. And after that, let's estimate the error as the absolute value of a difference between df of x and approximation. If error is greater than maximum, then reassign the value of maximum and increase the value of x plus equals h. This line just to output the value of x, value of a function, to the screen. Very simple program that computes the values of the first derivative on the interval from a to b. Function sinus x and df is cosine x. Let's run this program. Here is the table of the values. X, what's x, f of x. The next column is f of x. Then the approximation value and error. maybe it's better to output the caption of a table before the loop. The first column is x, the next column is x, and approximation to the error. I'll put it to the screen as a caption columns. Yes, x, f of x, approximation, and error. So the x moves from 0 to 1, and you see that the error is approximately 0.01, and the largest error equals to 0.00166. Okay. Well, if we look to these, we compute the first derivative, but the formula for the error is more or less the same. This one. If you look to this formula as usual includes two terms, the approximation and the error term. Again, the error term here, the error term has two components. First depends on h, the second depends on the derivative of the function. But here we have the third derivative. But h power 2. Can you guess what happens with the error if I decrease the step 10 times? It means at the first experiment, I use h equals to 0.1. And after that, I use the step that 10 times smaller, 0.01. What happens with the error? Can you guess? Also reduce, but how? What is the level of this? 10 times, or 10 times, or 100 times, or 1,000 times, or maybe 2 times. 10. Here, h power 2. The error depends on h in power 2. It means if I decrease the step 10 times, the error will decrease 100 times, h squared. I can denote this step as h1 and this step h2 equals to h1 over 10. It's smaller than h1 10 times. And if I substitute h2 here in this formula, I will have h1 over 100. So, yeah, 100 over 100. And the error becomes 100 times smaller. Let's check it. Let's check this theoretical estimation. H equals to 0.1. What is the largest error? 0.0016. It approximately equals to 10 power minus 3. Let's let's recall this. 10 power minus 3. After that, I decrease the step 10 times. The error becomes 10 power minus 5. The largest error, 10 power minus 5. 100 times smaller than in previous case. Let's decrease one more time. The error becomes 10 power minus 7. Also decreases 100 times. Okay, let's use the first formula. The first formula. Fx plus h minus f of x over h. I just corrected. Yeah, the first formula. F of x plus h minus f of x over h. If we consider the error term for this formula, the error term includes h power 1. It means that if I decrease step 10 times, the error decreases 10 times too. Let's check it. The error is 0.04. And if I decrease the step 10 times, 0.004, 10 times smaller. And again, I think this example shows you all the features. Well, please remember this value, 0.004. This is the error that we get with the formula, with 2-point formula, with the step 0.01. What error we have when we use another formula, 3-point formula? The error becomes smaller. I just select another formula for computations. And this formula looks very similar to the previous one, but we get the error 10 times smaller. So the result will be 10 times better. Okay, and let me show one more feature. Let's come back to the error estimation of the 3-point formula. Yeah. Well, we see that the error term, it includes h power 2 and the third derivative of a function. What function I should take that have the third derivative equals to 0? Can you give me an example of a function with a third derivative equals to 0? Polynomial of second degree. For example, x power 2. X power 2, the first derivative is 2x, second derivative 2, third derivative 0. Let's use this function as a test function, not sinus, because when f of x equals to sinus x, df equals cosine, third derivative, next derivative is minus sine, then minus cosine. We never get 0. But if we select the test function x squared, x times x, df in this case will be 2x, right? And let's run the same. Let's run the same program. Even I can select h equals to 0.1. The error is 10 power minus 16. At the one of the first lessons, I told you that all the computations on computer carried out not exactly, but with some small error, with some so-called machine error or machine epsilon. And the value of this error is 10 power minus 16. So actually, when we compute, if we try to compute the value of the derivative for x squared, actually we get exact value, like in this case. But on computer never can give you exact answer. Just in some, maybe in some particular case, like here we see that the answer is 0. But in all other cases, the answer is not 0. Well, it's very, very important. Is it clear why we see these values? We see these values because the derivative of the function equals to 0. As far as the derivative of a function equals to 0, this term equals to 0, and the 3-point formula gives us exact answer. If we compare it with the 2-point formula, the error term of the 2-point formula includes the second derivative of a function. Second derivative of x squared is not 0. If I here the 2-point formula, I'll get large error. The error equals to 0.1. If I reduce the value, the error equals to 0.01. So it's not machine 0. It's not a 0 value. But if I come back to the 3-point formula, we see the value that corresponds to machine 0, computer 0. Well, is it clear? Okay. Well, let's have a break now. And after the break, we continue and we consider some theoretical features of numerical differentiation. We consider how to derive numerical differentiation formula using interpolation polynomial. How to derive the numerical differentiation formulas. Now, let's have a break. And we continue at 10.50. I stop sharing and we continue the lesson at 10.50.
What's up? Did you go to class? Hi, Eto. I dey call you, you dey waka dey comot. No, you no get respect.
Well, let's start the second half of our lesson. This second half will be more theoretical part. The first lesson more practical, the second half more theoretical. And now let me share again my screen. Well, let's let's briefly review again the formula for numerical differentiation. Three main formulas that are written on the slides, that are written on the board. Two-point formula for the first derivative. 3-point formula for the first derivative, and 3-point formula for the second derivative. But the question is how to write the formula for numerical differentiation in a general case. Because here, these formulas can be considered as just some particular cases. This, and this. How to write a formula for numerical compute derivative in a general case. Let me remind you that the initial information is the values function at some points. These points can be denoted as x0, x1, x3, and so on, xn. It's written here on the slide. I just rewrite the same above. That we have the points x0, x1, and so on, xn. Generally, we denote these points x, this index, right? And we know n plus 1 values of a function at these points. f1, f0, f1, f2, and so on, fn. This is an initial information. The values of a function at some given points. But using these points, we can write Lagrange interpolating polynomial. If we take 2 points, we can write polynomial of degree 1. If we take 3 points, we can write a polynomial of degree 2, and so on. So we can write a polynomial Pn of x that can be considered as approximation to the function f of x. And as far as polynomial is close to the function, the derivative of polynomial be close to the derivative of a function. The first derivative. The second derivative of a polynomial will be close to the second derivative of a function, and so on. So the general idea that allows us to write any kind of numerical differentiation formulas, or even not numerical differentiation, but also numerical integration formulas, is to take the given points, to write Lagrange interpolating polynomial, or it may be not Lagrange, maybe Newton, but write an interpolating polynomial, and then compute the derivative of this interpolating polynomial. These formulas can be applied for any x, for any value of x. But these formulas becomes very simple when x is the same as one of these x's, x0, x1, x2, or any other x. In this case, the formula will be very simple. It's written in the form of the formula with star. The derivative of a function approximately equals to sum of the derivative of derivatives of auxiliary polynomials Li multiply the function value f of x. And let's consider this simple case for the linear polynomial. Let's review the material, the topic that we consider previous lesson, Lagrange interpolating polynomial, linear interpolation. Note that we have 2 points, just 2 points, x0 and x1. Just 2 points. If we know 2 points, we can find a polynomial of degree 1. The formula for this polynomial is written here. It's L0 of x times f of x0 plus L1 of x times f1. P1 of x equals to L0 of x times f0 plus L1 of x times f1. Again, let me remind you that f of x0 and f of x1 are constants. The functions here are L0 and L1. And this formula has very simple derivative. P1 prime of x equals L1 prime times F0 plus, or L0 prime plus L1 prime of x times F1. According to the rules of differentiation, the derivative of sum is sum of the derivatives, and derivative of a function multiplied by a constant is the derivative of the product function times constant is equals to derivative of a function multiplied to this constant. And actually, to find the derivative, we should find the first derivative of L0 of x and first derivative of L1. Please look to the formula of L0. What is the first derivative of L0? The formula for the auxiliary polynomial L0 is written here on this slide. What is the first derivative of L0? What? X0, x1 are constants. The variable is x. What is the derivative of L0 of x? No, it can be, it's x here. X0, x1 are constants. X0 and x1 are constants. X is a variable. How to find the derivative of this function? L0 of x equals to x minus x1 over x0 minus x1. Derivative. These are constants. According to the rules of differentiation, we can move the constant outside the sign of the derivative. Right? 1 over x0 minus x1, x minus x1 derivative. Because x1 and x0 are constants. What is the derivative of x minus x1? No. What? 1. Not x, but 1. x0 is a constant, and the derivative of x0, oh sorry, x1. x1 is a constant. Derivative of x1 is 0. Derivative of x is 1, so this is 1. And their derivative of L0 of x is 1 over x minus x0 minus x1. 1 over x0 minus x1 times f0. This is the first. This is the first term. What we have here for the second one? L1 prime of x. L1 equals to x minus x0 over x1 minus x0. What is the derivative of L1? Yes, 1 over x1 minus x0. So we have plus f1 over x1 minus x0. And the last point, if we denote the difference between x1 and x0 as h, usually h is the usual notation for the distance between points, the step, distance between 2 points. x1 minus x0 will be h, and x0 minus x1 will be minus h. And we have f1 minus f0 over h, where h is a distance between x0 and x1. Is it clear? So let's compare this formula that we derive from interpolation polynomial with the formulas that we used earlier, with this one. If we take the value of x as x0, what we have here? F of x0, f of x1, x0 plus h over h. So we derive the formula number 1. But here we derive it from the definition of the derivative. And the second case, we derive it from interpolating polynomial, from interpolation. But we get the same formula. Okay? Now, let's consider the second case. This is a polynomial of degree 1, but we can consider the polynomial of degree 2. It's not written here because here on the slide is written just a formula for the general polynomial of n degree. Let's consider one more point, x2 and f2, right? And suppose that the distance between the points are the same. x1 minus x0 is h, and x2 minus x1 is also h. The distance between these points are the same. Now we can write an interpolating polynomial of degree 2 using these 3 points. How to write it? P2 of x equals to L0 of x times L0 plus L1 of x times F1 plus L2 of x times F2. Only the formulas for L0, L1, and L2 will be different. What is the formula for L0? According to this general case, for L0 should be x minus x1, x minus x2 over x0 minus x1, x0 minus x2 times f0. This is the formula for the first term, L0 times f0. Before we write the next formulas, let's immediately simplify it. How we can simplify it? We can use notation h as a distance between points. If h is a distance between x1 and x0, how I can rewrite this product? If h is the distance between x1 and x0. So these points, x0, x1, x2. This is h and this is h. How I can write the denominator? X squared. What? H squared. No. X0 minus x2. It's not h. X0 minus x2. What is the distance between x0 and x2? 2h, right? No, minus 2h, 2h, right? You forget 2. So it's not h squared, but 2h squared. And here the h will be with minus, and 2h will be with minus. But minus on minus gives us plus, and we will have h 2h squared plus the second term L1 x minus x0 x minus x2 over x1 minus x0 x1 minus x2 times f1. The second term of Lagrange interpolating polynomial, I write it in general form, and again we can simplify the denominator using h. What I can write here? x1 minus x0, x1 minus x2. H squared. No.
Minus h squared.
Minus h squared. Minus h squared. x1 minus x0 is h, but x1 minus x2 is minus h. So here I can write minus h squared and plus the last term L2 x minus x0 x minus x1 over x2 minus x0 x2 minus x1 times f2. The last term in Lagrange interpolating polynomial. Oops, I close. The last term in Lagrange interpolating polynomial. How I can simplify the formula? X2 minus x0, x2 minus x1. Two h squared, like in the first case. 2h squared. Okay. This is the formula for the polynomial. What we should do next? let me switch to the presentation, to another presentation. According to the formula with star, the derivative of a function approximately equals to derivative of polynomial. So we should write the derivative of a polynomial. I do not rewrite this formula, but in your papers you can rewrite it. That this is a p2 of x, but let's find p2 prime of x that equals the derivative of this formula. How to find the derivative of the sum of these three terms? What is the derivative of sum of the function? If you have the derivative of some large formula, and this formula consists of sum of several functions. How to find this derivative? It's a question. How to find the derivative of sum of two functions? It's sum of the derivatives. It's g of x plus f of x. Sum of the derivatives, derivative of the sum equals to sum of the derivatives. That's why I can move the sign of the derivative inside the sum from here to each of these terms. Again, you can rewrite it, but on the board I just write like this: derivative, then derivative of this, and derivative of this. Now, if we look to each of these square brackets, if you look to each of these square brackets, we can see that each square bracket has the same structure. X minus something times x minus something over h squared multiply some coefficient times value of the function. But let's remember that h and f are constants. And again, what is the rule of differentiation? If you have a function f of x and a constant, and if you find derivative constant times f of x, it equals const times s prime of x. So you can move the constant outside of the sign of the derivative. So this constant f over 2h can be moved outside the sign of the derivative. And actually, you should find the derivative of x minus x1 times x minus x2. And similar derivatives in the last cases, x minus x0, x minus x2. X minus h1, x minus x2 derivative. Let's consider this. particular case, x minus x1, x minus x2 derivative. How to find this derivative? We extremely simplify our large formula, but we cannot simplify it more. How to find this derivative? Again, it can be computed using several ways, but the most simple way is to remember one more rule of differentiation. One more rule of differentiation. Let me write it below here. That f of x times g of x derivative. Do you remember what is the derivative of product of two functions? Derivative of sum equals to sum of the derivatives, but derivative of product no, it's more complex formula. It's the derivative of the first times second f prime times g plus g prime times f. This is the rule of differentiation of two functions, of the product of two functions. These rules, you can find it any somebody use French language here. Rules of differentiation. Derivatives of powers, exponential, and this is constant rule, sum rule, product rule. Do you see it? Product rule and quotient rule. We use this rule. G f times g prime equals to f prime times g plus f times g prime. What will be the result here according to this rule of differentiation? Right, but it's better to write it in the form just x minus 1 plus x minus 2, x minus x1 plus x minus x2, right? x minus x1 plus x minus x2. So in this case, it's very simple to find the derivative. Just replace the product with plus for all the terms. I just corrected here. I just corrected. Let me just replace and write here plus, 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 and plus. Okay. Now, finally, we obtain the formula for the first derivative of the polynomial. After that, you can substitute here any x that you want. And if you substitute this x, you get the approximation to the real derivative at this point x. But you can select any x that you want. But in some cases, when we select this x as when we select x that is the same as x0 or x1 or x2, this formula becomes very simple. This formula is large now, but if we select the x that equals to one of these three x's, this formula becomes very simple. Let's select x1. P2 prime of x1. So you should substitute x1 instead of x. What happens? X1 minus x1, 0. X1 minus x2. What is x1 minus x2? X1 minus x2. It's not h. Minus h. So we have minus h over 2h squared times f0. This is the first.
x1, x2, h of x.
X1 minus x2. So x1 minus 5 minus 10. 5 minus 6. X1 is less than x2. 5 minus 6. Put here the concrete values, concrete numbers, and situation becomes clear. Minus h. Okay. The second. X1 minus x0. Let's consider the second square bracket. X1 minus x0. H. X1 minus x2. Minus h. This is 0, and all of these terms is cancelled. So the formula becomes very, very simple if we select this x1. And finally, let's substitute here x1. This is h, and 0. H over 2h squared times f2. The central part is cancelled. Here, h over h squared, we can cancel one h. And the same for this one. And what we have? F2 minus F0 over 2H. Very, very simple formula. And moreover, this simple formula will correspond to the 3-point formula when x equals to x1. Right? And if we consider x equals to x1, we have x1 plus h equals x2, x1 minus h equals to x0. We have f2 minus f0 over 2h. Again, we derive the same formula from another approach. But this approach is more general. It allows us to derive different formulas. Here we find the formula for value of x equals to x1. But let's do the same for x equals to x0. P2 prime of x0. What should we do to find this formula? We should substitute here x0. Please do it by yourself. And after that, we check your result. P2 of x0. Here we substitute x1 and to get this very simple formula, I ask you to substitute x0. Well, did you get some results? Yes, it's. Yes, I think it's right, but you get here to. Second, you have h over h squared, h over h squared, 1h in pencil. Well, there are a lot of formulas that can be derived using this approach. Unfortunately, I don't know how to find it in English because I know only this page in Russian Wikipedia where all of these formulas are listed. We find the formula for the first derivative, f of x1 minus f of 0 over h. Then the next case, the formula for 3 points. And f prime of x1 equals to f2 minus f0 over 2h. We already get it. Your case that I ask you to do is f prime of x0. And we have minus 3 f0 plus 4 f1 minus f2 over 2h. This is error term. But the formula is written here. Check your results. You should get the same. Minus 3 f0 plus 4 f1 minus f2. And also, the same approach can be applied to find P2 of x2. P2 of x2. Just as a home task, find their f P2 of x2, and you should get this result that's written here. F0 minus 4 f1 plus 3 f2 over 2h. Well, I think the general idea how to get the formula for the first derivative is clear, but the same approach can be applied to find high order, the formulas for the high order derivatives. We already discussed about it. What is the second derivative? The second derivative is the first derivative of a first derivative. We can find a first derivative, and after that take a derivative of this first derivative, and we get the second derivative. This is the formula for the first derivative of P2 of x. Let's find P2 second derivative of x. Let's find the second derivative of x. How to find it using this? The same idea. We can take the first derivative of this large sum. The derivative of the sum equals to the sum of the derivatives. Then we have constant multiply to the function. We can move constant outside the sign of the derivative. And actually, finally, we should find the derivative of x minus x1 plus x minus x2. What is the derivative of x minus x1 plus x minus x2? 2. Situation is very, very simple. Is 2f0 over 2h squared. The second term, again, we have 2 minus 2f1 over h squared. I mean minus here. And the last term, we have 2 plus 2f2 over 2h squared. 2 here is cancelled. We have the same denominator. And finally, we have f2 minus 2f1 plus f0 over h squared. We obtain this formula as a second derivative of the interpolating polynomial. But if we compare this formula with the formula that we used previously, the formula star on this slide, you see that this formula is the same when x equals to x1. f2 minus 2f1 plus f0 over h squared. And after that, but well, this is also very important feature. No x's here, just constants. f2, f1, f0, h. So e second derivative of x equals to a constant. That's why the third derivative will be 0. We cannot estimate third derivative using only 3 points. To estimate the third derivative, we should add here one more point, x3, and write not a polynomial of degree 2, but a polynomial of degree 3, and compute the first, the second, the third derivative of polynomial of degree 3. Well, finally, the general approach of numerical differentiation. We consider the set of points. We write an interpolating polynomial, and we find the derivative of this interpolating polynomial. And this derivative will be more or less close to the derivative of the function, of the because we don't know the real derivative of the function. We can only find this approximation. Let's look how the formula for the second derivative works in on computer, in a program. Let's do it. Let's do it in this simple program. This is our first derivative. Let's come back to the sinus. For example, this sinus, sine, cosine. Let me copy and declare one more function, ddf. the second derivative of the derivative of f. What is the derivative of cosine? Sinus. So the actual value is minus sinus. Okay, now let's use here df of x, and for the approximation, let's use this 3-point formula for the second derivative. F of x plus h minus 2 times f of x plus f of x minus h over h squared. Okay. Now, let's use the step 0.1 and let's run this program. We see that their approximated value is very close to the real value of the second derivative. The error is 7 times 10 power minus 4. Let's take the step 10 times smaller. And the error becomes 10 power minus 6. And again, let's consider the formula for the error. This formula includes the fourth derivative of a function. It means if I take here a polynomial of degree 3, the derivative of polynomial of degree 3, the fourth derivative of polynomial of degree 3 will be 0. And we get their exact value. Let's check it. Let's take as a function not sinus, but a polynomial of degree 3, x times x times x. What is the derivative? X power 3. X squared. And the second derivative, six x. Let's check. Yeah, we see that their error is very small. It approximately equals to machine 0. If we compute this value on a paper, using pen and paper, we get exact 0. But on computer, we have very small value, 1 times 10 power minus 14. Very small value. Well, any questions about formulas for numerical differentiation? No questions. Well, let me remind you again that the information about numerical differentiation you can find in the books that I sent it you on the first lesson, or you can find in Wikipedia. You can find all of these formulas. Here I find it in Russian, but you can find it in English when you open the page related with derivatives or numerical. Numerical differentiation. You can find all of these formulas. Maybe the main difference. Yes, the main formulas, you can find it here. Well, as I know, the next lesson, on the next week, it will be ordinary lesson. According to our schedule, we will start 10:50. We have only one lesson. And on this one lesson, we consider formulas for numerical integration. And the lesson next week after week, so the lesson on May 10, as I know, May 10 it will be a holiday. May 3 it will be ordinary lessons, and May 10 will be a holiday, so we have two final lessons here. And so May 3 we consider numerical integration, and two last lessons we consider two topics: least square method and numerical solving of differential equations. But to start the next lesson, let's briefly consider what is integration. Let's consider it now. Do you remember how to find the numerical integral, the exact value of integral? Do you remember or no? No. Integral f of x dx from h to b, it equals to f of b minus f of a. Do you remember this formula? Yeah. Yes, of course. Usually students, this is the usual answer on the exam. No, I don't remember. But when I write the formula, oh, sure, I remember it. What is capital F? Is anti-derivative. F of x prime also f of x. So you should, to apply this formula, you should know anti-derivative, so-called anti-differentiation. For example, if we consider integral from 0, or not from 0, from 1 to 2, x dx, So x is f of x, small f of x. what will be a capital such antiderivative of x? Such function, the derivative of this function equals to x.
X.
What? Yes, you can write. So f of x equals to x. What will be here? F of x. No. No. Please find derivative. Find derivative of x. No. Please find the derivative of the function that you write. It will not x. Yes, try to find the derivative of this function. 2x one, 2 times 1 over 2. It's not x. It's not x. The idea is more or less correct. What function we should take to get x as a derivative? You are on the right way. The formula is very close to the correct answer. Yes, f of x equals to 1 over 2 times x squared. If you find the derivative of 1 over 2 times x squared, it will be x. 1 over 2 x squared equals to x. So the integral will be f of x, f of b minus f of a. And usually it's written also like this, f of x, a, b. So I can write 1 over 2 x squared, 1, 2. And it equals 1 over 2 times 2 squared minus 1 over 2, 1 squared. And it equals 3 over 2. Three over 2. But we can apply this approach only when we know antiderivative. And this problem is more complex problem as differentiation, because there are a lot of functions that doesn't have antiderivatives. The function is very simple continuous function, but it doesn't have antiderivative. And we cannot apply this approach, but we can find the integral using some numerical formula. Well, and this will be the topic of our next lesson. This will be the topic of our next lesson. Well, today, let's finish our work. I stop sharing. I will send you the video file of the lesson later. The presentation of this lesson I sent it you previous week. Next week, our topic will be numerical integration. That's all. Let's finish our lesson. See you next week. 10.50.